Assalamu alaikum wa rahmatullahi wa barakatuh, and good afternoon, everyone. Welcome to UTM Engineering Distinguished Lecture Series, which is organized by Faculty of Engineering, Universiti Teknologi Malaysia, Johor Bahru. My name is Fuad Abdul Jalil from the School of Computing, Faculty of Engineering, UTM Johor Bahru. Okay. I will be the host and the moderator of the today talk. Today we are very grateful and very fortunate to have one of our research collaborators, Professor Dr. Adel Ben Mnaouer from Faculty of Engineering at the Canadian University Dubai in the United Arab Emirates. Dr. Adel Ben Mnaouer received his BSc degree in computer science from the École Supérieure des Communications of Tunisia in 1985 and the Master of Engineering along with PhD degree in electrical and computer engineering from the University of Hokkien and from Yokohama National University, Japan in 1993 and 1997 respectively. Dr. Ben Mnaouer has served as associate professor and acting dean since 2010 until 2011 of the College of Computer Engineering and Information Technology at Dar al-Ulum University, then as a Vice Dean of Research of the same college. He joined the Faculty of Engineering of the Canadian University Dubai as an associate professor in September 2012. Okay, so currently he is serving as full professor in the same faculty of the Canadian of Engineering at the Canadian University Dubai. His research interests are in the area of the protocol design and analysis of wired and wireless network, wireless sensor network, wireless body area network, MANET, FANETs, and FANETs, Internet of Things, and cyber physical system, clustering, and grade and cloud computing. Dr. Adel Ben Mnaouer is the recipient of 4 major QNRF projects worth $30.7 million focused on harnessing the power of wireless sensor network in remote ubiquitous healthcare systems, in air quality control, structural health monitoring, in developing new communications protocol that are better equipped to serve specific target application fields. He is active in chairmanship, editorial board, TBC, and organizations of a score of top-class international conferences and symposia. Dr. Adel Ben Mnaouer is a senior member of the IEEE Communications Society. So the topic of the today session is going to be on the multi-parametric clustering algorithm designed for flying ad hoc network. Okay, so those who have questions, please write them down in the chat or in the comment sections on Facebook, and Professor Dr. Adel will answer them at the end of this session. Now, I would like to invite Professor Dr. Adel Ben Mnaouer to share his slides and deliver his speech. Prof. Dr. Adel, the stage is yours.
Yes, do you see the slides? Is it okay?
Yeah, we can see.
Okay, thank you very much for this nice presentation introduction. I am very much honored and I have a great pleasure of joining you today to give this lecture that is will be centered on the new, let's say, protocols designed for this flying ad hoc networks, new type of networks. Now, I need to move to my own slides. Okay.
Then, yes,
So,
okay.
so today, I mean, the title of the talk will be a multi-parametric clustering algorithm designed for FANETs. So we need to propose some, I mean, methods for, let's say, having a better communication of information and data inside this flying ad hoc networks. What do we mean by flying ad hoc networks? We mean, I mean, UAVs or drones, as they are known, that are flying in an ad hoc fashion that is governed by the mission that they are assigned to, and they are connected, I mean, between themselves through, I mean, their own means of communication on a hop by hop or a point-to-point communication to form, I mean, a moving and a flying network. This network can be connected to the internet if, I mean, one of the members of the network can have any, I mean, connection to the internet, for instance, and that's what will be, I mean, talking about later on. I mean, otherwise it can be an ad hoc network that is independent and flying in coordinating, I mean, the exchange of information and data while flying, I mean, for a specific mission. It has lots of application in the field of monitoring in border patrol, in monitoring, I mean, marine life, or I mean, sea life, or I mean, forest life, for instance, and monitoring crowd, monitoring basically several, I mean, aspects of interest to the humans, for instance. Now we move on to the content. So for the content, we are going to talk about the evolution, I mean, from what has been called before as MANETs up to reaching this, I mean, FANETs. Now the MANETs, basically, we are going to, I mean, introduce them. They are mobile ad hoc networks that are, I mean, not necessarily flying. And through time, we have reached, I mean, to the application of the concept of ad hoc networking into the FANETs. So next, we'll give a characterization of the common problems of these FANETs and MANETs, and again, another type that is called a VANET. A VANET is a vehicular ad hoc network. So we have always this feature of ad hoc networking, that is a networking that is not relying on, I mean, infrastructure. That means not relying on a specific networking infrastructure to allow members of these networks to communicate. So they rely on themselves to communicate with each other without any help of any networking, I mean, facilities. Then we'll talk about this concept of clustering algorithms and why do we need to, I mean, have some clustering. So from its very name, clustering means creating cluster. Creating cluster means grouping a number of these nodes, whether they are, I mean, normal, let's say, communicating nodes like laptops or mobile phones or whatever. I mean, or I mean, in the case of vehicular networks that are made of, I mean, communication equipments within, I mean, moving cars, moving vehicles, or to the FANETs, which are basically, I mean, moving UAVs or drones. So we need to have, we have a need for a clustering that has started with the advent of MANET that we need to, I mean, address. Now, later after that, so we'll be talking about the EMAS, a novel clustering algorithm for FANET that we have recently, I mean, proposed and has been published in the IEEE, I mean, Access journal just recently. Then we'll speak about it, we'll introduce it and give a performance evaluation. Then we conclude and give some future, I mean, perspectives. Now, directly to the MANET. So basically, MANET, as I said, as you see on the left, I mean, a MANET is a collection of, I mean, laptops or mobile phones, or devices that can communicate wirelessly, and being able to move, so that they call Nammanat. If they don't move, they are just an ad hoc network, that is made by setting these equipments to communicate together, and not to communicate through an access point, for instance. So the communication link between them is just the wireless transmission that they have between them. And then for a node to communicate with another node, it has to be in its proximity. Otherwise, the communication has to hop through intermediate nodes until it reaches a target node. Now, the same concept has been moved, to the realm of VANET, or intelligent, transportation system, it's called sometimes. That included basically a communication between cars, which we call vehicle-to-vehicle communication, a V2V, or from cars to the infrastructure that is talking to those base stations, for instance, that we usually call RSU, that is roadside units that are established on the side of the road to help the communication basically go on between these moving cars. We can have also a V2H communication, that is communicating with humans, or H2V, for instance, that is communicating with the mobile phones and so on. We can have also a communication that is called a V2X, that is communicating with anything that is that can be communicated with basically in the environment. And that's path of research has led basically to the this connected cars, to the autonomous vehicles, and so on. Now, after a huge, let's say, success of the MANET, and the big research that has been basically implemented for MANETs, there was a need to move into the wireless sensor networking, the WSN. So wireless sensor networking has erupted as a new, needed area, specifically after the tsunami that has hit, Asia in 2005, and there was a need basically to have means to, to observe and to monitor the sea, and monitor anything else that can, cause a danger to the human lives. And the huge, success of research has been done in that area. Then recently, basically, with the advent of drones, and with the advances in, UAVs and drones, and with the public access to these, a huge, basically, the legacy of what has been done for these previous three type of architecture, have moved basically to support, the flying ad hoc networks. That is basically the concept of having a swarm of, drones or UAVs flying together in a mission, and doing some, basically, operations and missions of monitoring and so on. So basically, MANET, WSN, VANET, and FANET, all of them, they have some common problems. One of the problems is basically data dissemination towards sync nodes. The sync nodes is the node that will be, doing the processing of the data to extract some information out of it. That's, one of the basic tasks. Then we have also, a task of maintaining a topology stability, basically, so that, we can still have, a network that is well connected. And this requires basically the concept of efficient routing protocols that are meant to route data, or to, find the right path for data from one point to, a destination, until we reach this sync nodes. And along with that, we clustering algorithms have been found by the research community to be very much useful in, facilitating the role and the task of the routing protocols for, having the routing task being, much more efficiently, executed. Now, this involves definitely, some, concept of energy awareness. So you have to be aware that most of these nodes are basically, depending on batteries that have limited life. So we need to be efficient in the way we use energy. And then also we have to have, a concern for insurance to, ensure the CIA, requirement of confidentiality, integrity, and availability of data. Now, the FANET, as an introduction, it is a flying ad hoc network. It is a network that incorporates several UAVs flying in a coordinated fashion and collaborating in an ad hoc manner. So these are characterized by what we call peer-to-peer or hop-by-hop communication, as we said. I mean, you need to hop through, I mean, a neighbor, I mean, and pass the communication to a neighbor so that you can get into, I mean, a further neighbor that your, I mean, transmission facilities does not help you reach. They are, I mean, characterized by higher mobility than MANET and FANET nodes. They are flying at the, I mean, the drone speed, basically, in the air. They are deployed usually in squad formation in 3D plane. And they have very fast, frequent, and dynamic network topology changes, which is the biggest challenge to this, I mean, flying networks. Now, the FANETs and Internet of Things. Now, Internet of Things are basically when these type of things that are coming from the physical world that have been equipped with communication, wireless communication, and with computing, I mean, facilities. So they can do some computation, then communicate. And they're coming from the physical world, and like, I mean, a temperature sensor, for instance, or a proximity sensor, or, I mean, any camera, for instance, that is sending, I mean, images and so on. And they have a relationship with the drones in a sense that, I mean, they are being, I mean, attached, I mean, to the drone, I mean, for serving several purposes of, I mean, tasks that are required, I mean, for the drone to accomplish, and it needs basically to get this information. So drones or UAVs can be loaded with, I mean, a set of IoT devices that adds an additional burden of power and computing. We need to power all these, and we need to basically, I mean, gather the data from these, I mean, devices, and then we need to transmit the data to others. Now, the drones themselves are equipped with, I mean, batteries. So their flight time is usually very much limited. So, I mean, with this environment, they are forming what we call a flying multi-parametric, I mean, IoT platform. That's their own. The first task is to collect data locally from, I mean, at the drone level, for instance, and then, I mean, to communicate this data, I mean, to, I mean, first to merge it with other UAVs data that is being, I mean, requested to be forwarded to the sink if you are in the path to the sink, and then to, I mean, merge the data and clean it up, and then remove redundancy and send it to the sink for further, I mean, processing. Now, as we have been talking at the beginning, the title of the talk is how to design and how to make, I mean, good clusters of these, I mean, flying, I mean, drones, so that it will make basically the task of, I mean, monitoring, basically, that is the main task of drones, I mean, very much, let's say, I mean, smooth and long-lasting and efficient in terms of energy, in terms of, I mean, let's say, coverage. Now, clustering is, in a sense, dividing the geographical region to be covered into small zones with one selected node as, I mean, a cluster head. So we have a number of nodes now within a certain region. We choose one of them to be a cluster head. The cluster head will be the one that will be, I mean, receiving all the data from all the cluster members that we will call, and then it will channel that data to another, let's say, cluster head. So the cluster heads being selected out of a set of nodes in covering certain geographical, I mean, region. They will be communicated together to, I mean, forward the collected data, the aggregated data, I mean, towards a sink, I mean, node that is, I mean, located somewhere. Now, the benefits of clustering, for which we get what we call a first-hand collection of data within the clusters, very fast and in one, I mean, specific direction. So you don't need to find out to whom are you going to send the data. You know your cluster head, you need to send it to it. Then it will simplify the communication process greatly and make it more efficient. And the main issue here is how to choose the best fit for serving a CH among all those, I mean, candidate, let's say, I mean, nodes. So this basically will lead to a better energy efficiency. I mean, let's say choosing the one that has the best energy or the one that has the best position, and then that role can be later on, I mean, exchanged among the other members, so that we can have a load that is balanced among all the nodes that are flying, so that we don't lose basically any of the nodes, while we are in operation. Now, the cluster head role, is decided dynamically to achieve specific operational goals. For example, we need to achieve higher throughput, more data to be put through the network, better battery usage to, increase the longevity of the network, for instance, better load balancing, between the nodes, better what you call, medium access control functionalities that are, facilitating the routing function and the communication in general between these nodes. Now, the desirable feature of a good, algorithmic or clustering design, calls for an ideal cluster size to handle expected communication load. So you have a certain area to cover, a certain data to come to gather from a certain area. So you need to have, the required number of cluster members that can, take care of that load to, be passed, to the head and then to the destination, sink. Now, it has to have, a fast finder of the best CH. So it has to be, a fast finder for the best CH as a procedure or as an algorithm, to find the cluster head. Now, it has to have low complexity in the CH selection process, and it has to ensure maximum network longevity and stability. Then again, it has to guarantee, safe distance between nodes so as to basically, avoid any collision, for instance, and that's mostly in the case of VANET and FANET as they are moving nodes. And the last thing is to minimize the routing overhead. The information that is sent basically as an overhead, not part of the data, but it's just, to help the data move on within the network, and then to maximize the throughput, maximize the data that is put through the network, up to the sink. Now, the challenges that are ahead of the design for clustering basically is first, the complexity of the coordination task between nodes in presence of large UAV swarm. When we say basically the UAVs that sometimes they're called, Internet of Drones, sometimes they're called, formally, FANETs, but another basically naming is basically swarms of UAVs, like, swarms of, bees and so on. Basically, they are flying in a swarm formation, and this swarm formation basically, if the number of UAVs is quite large, then there is a complexity of coordination of tasks between them. Then the other problem is the intermittent connectivity. If the flying patterns are not, fixed and are unpredictable, then we can have, an intermittent connectivity if the speeds are not stable and the levels and the planes where they are flying are not, maintained. We have also the limited air endurance due to the limited power storage, that is basically the battery life, and the possible data duplication during forwarding that will usually use the energy of these drones and make, an energy loss, for instance. Thus, basically what we need an efficient clustering design to control the flight formation in large UAV swarms and ensure safety, stability, and fast communication. So these three, features are very much needed: safety, stability, and fast communication. Now, characterization of the cluster layout now. So we are talking, as we said before, about a number of nodes, which we usually call, normal nodes. And if they are normal nodes, they are not had, we call them cluster members. So we define the region of, the geographic region where we are going to consider a number of nodes, and then we have to select among them, a cluster head, and then all the other members, if they're not selected as cluster head, they will be automatically, included in the cluster membership as cluster members. Then only the CH is responsible for the communication. First with its CMs, with its cluster members, to get the data out of them, and then to communicate with the peer CH for the sake of aggregating data towards a sink. Now, the sink can be what we call a lead CH, basically a specific a drone that has specific characterization that's stronger than the others, has more, let's say, computing power, more, let's say, battery life, storage and so on, so that it has a communication or a connectivity to with the base stations, and that is a ground base station that is needed, to collect the data and then to basically deal with it. Now, conventional clustering techniques they are not really, applicable to FANETs, because, FANETs has its own different, let's say characteristics. Like, it is the nodes are usually flying in 3D motion that is very fast, and it's not, and the conventional one are mostly designed for 2D, planes. Then the conventional clustering techniques also are not expecting extremely high mobility, like what we get in FANET. So MANET and WSN, for instance, they are not made for that. And the node collisions are not considered as specifically for MANET and WSN. VANET also is there, but these are the collision control is not part of the network, is part of the driving task. So it is not considered. So all these are basically making the conventional clustering techniques not to be applicable for FANETs. Thus, new design methods considering the above lacking features are definitely needed. Now, the approach of recent contribution for CH selection, recent solutions or clustering solution they have focused on considering the average distance between nodes in order to select the CH. That means you are considering basically the distance between nodes, and based on that we select a CH. And then another thing is the node degree of connectivity, or what we can call basically informally node vicinity density. How much dense is the vicinity of a certain node? So that's we call a node degree of connectivity. Now, in that sense, basically the search selection is based on sequential search to find neighbors in the conventional methods, basically. And this will make basically the search for neighbors, to be sequential. That means it will increase the probability of collision, specifically in the case of a dynamic network such as FANET. If you don't consider basically, a safety distance between the nodes, and then you just, assume that there is, the nodes are in the transmission range of each other, and that's it, then you have, the possibility of getting, collisions between the nodes, and having part of the network to fail, for instance. Now, two recent contributions are going to, cover quickly that are forming basically the essence of our, let's say, approach for the design and for our, proposed, EMAS protocol. The first contribution is by, Adel et al. Basically, energy-aware cluster-based routing in flying ad hoc networks has been published in 2018 in Sensors, journal. The protocol is called EALC, and its main contribution is it is proposing an efficient clustering algorithm to enhance routing and energy saving. It adjusts the transmission power of the UAVs by anticipating their operational requirements, and it uses a variant of the k-means density clustering algorithm for selection of cluster heads. And the k-means density clustering algorithm is a well-known clustering method basically for making two good clusters for depending on the density of the distribution of the nodes inside the considered network area. It has obtained optimal cluster head, or the obtained optimal cluster heads enhance the cluster lifetime and reduce the routing, overhead. So it has desirable features, but as we will see later on, we have found some serious flaws in the, is not flaws, is basically some shortcomings of the parameters that I've used for this. That makes it not 100% applicable in the case of FANETs, and we try to modify, improve these parameters, and based on that we have proposed our algorithm. The second one is the BICAF, bio-inspired clustering scheme for FANET. It is a clustering scheme that is based from inspiration from the BioLife, for instance. So the main constraint or contribution, sorry, of the BICSF is it proposes a bio-inspired, clustering scheme for FANET. Proposed scheme uses energy-aware cluster formation and cluster head elections on the basis of the glowworm swarm optimization algorithm. The glowworm is those, fireflies that emit light. So these flies, they emit different intensity of light, depending on the other parties that are in front of them, and depending on the environment, the light environment around themselves. So it has given basically researchers insights on how to cluster basically these how they cluster themselves. For instance, this glowworm uh, uh, insects, for instance, and how they are using those intensity control to make an efficient clustering. So they got good results out of it. So they propose an efficient cluster management algorithm using the behavioral study of the krill herd optimization. Again, the krill is the type of shrimp that is found in the sea. They have also their behavioral properties that have made them to be their life or their methods to be used for optimization. Now all these are what we call evolutional algorithms that are based on the power of nature and the behavior of the nature that helps engineering to do better solutions. Now for route selections, authors propose a path detection function based on the weighted residual energy, number of neighbors, the distance between the UAVs, and for efficient communication, basically. Okay. Now our problem formulation here. The critics of the previous related work first. So the previous works, they had relied on simple equations for neighboring, considering only transmission range as the only condition for neighborhood. And that's basically the example that you see here. We have a transmission range between two nodes. If they are in the transmission range of each other, then they can be candidates to be chosen in the selection of the cluster head, which is basically poses the danger of being too close, and the danger of allowing a collision to occur, as these drones they drive or they fly at a very high speed, for instance. Now it applies to VANETs, but not to FANET. If you apply those transmission range only, it can be done with MANET and VANET, but FANET, there is no safety guarantee that can be given. Now, the EALC and then BICSF algorithms, they have used, again, the node degree parameter as one of the main parameters in the fit function to find a fitting candidate to be used for the as a cluster head. This does not take into consideration the respective relative position of these neighboring nodes as well. Now, for this sake, only stable neighbors situated at a safe distance from the current node must be considered neighbors to ensure safety and avoid the possibility of collision, and then to be considered to be, one possible cluster head. Now, to overcome this inefficiency, we consider UAVs at a safe distance and belonging to the node's neighborhood set, NI, to build a relatively stable cluster structure. And that brings us to the main purpose of this work, basically, is to propose an improved clustering approach, implementing new parameter setting to ensure stability and safety for efficient inter-UAV communication FANETs. Now, getting more in detail and showing some basis of the analytical modeling of this. So the UAV network is given or is modeled as an undirected Euclidean graph G of a set of vertices that are the nodes, and a set of edges E that is representing the set of links of the graph when you have the nodes are in the transmission range of each other. R represents the transmission range between the two nodes UAV, and it is assumed that R is the same for all UAVs. That means they are all using the same type of transmission facility, so they have the same range of transmission. Now, for any pair of nodes UV, if the distance between UV is less or equal than R, then UV are in the set of edges. That means they can communicate with each other. UAVs are assumed to follow specific mobility patterns during their movement on the same altitude and dictated by the mission. We suppose that they are flying on the same altitude and they are following, I mean, strict, let's say, guideline there. Now, UAVs communicate by exchange of hello messages that includes the ID of the node, the velocity, the speed, position where it is positioned, the direction to the direction that is flying to, and I mean, in addition to that, basically some, I mean, indication of fitness to be, I mean, a what you call a cluster head. That is computed by all nodes, and the one that has the lowest, I mean, let's say, I mean, value of that fitness factor, then it is automatically elected as, I mean, a cluster head. Now, this is the safe distance, let's say, safeguards that we have put in our, I mean, approach to make sure that, I mean, the nodes are, I mean, in safe in terms of, I mean, collision. So as you can see here, I mean, we have the central node is the one that is being considered as, I mean, it can be any of those nodes basically, as finding the nodes that are, I mean, can be considered as neighbors to it. So first we have, I mean, from the node till the outer ring. So we have the transmission range R. And then, I mean, from the, I mean, we have another parameter delta, basically, that is, I mean, within from the distance between, let's say, the nodes themselves. It should be greater or equal than this, I mean, delta here, okay? That if it is not maintained, so we are in the case or in the risk of collision. So basically, as you can see from this setting, for instance, that, I mean, this node CH2, I mean, it is I mean, safe with regards to all the neighbors. So that means all the neighbors, and with itself, they can be candidates for, I mean, to be, I mean, selected as cluster heads. Now, for instance, I mean, in this case here on the right ring, we have inside the inner ring, we have two nodes that are, the distance between them is less than delta, then these two nodes are in the risk of colliding. So only, I mean, one of them, I mean, they will disregard each other, but basically as potential, basically members of the, I mean, to be selected as I mean, as cluster head, for instance. So the main condition is to have the neighbor nodes being at a distance of r minus delta to be sure that they are, I mean, in the transmission range on one side, and then they are not close enough to, I mean, cause any danger of collision. Now, we continue with the analytical modeling. This set of R neighbors of a node I that is basically forming what we call the vicinity density. And I can be expressed as, an I is the set of nodes Vi and V, such as the distance between I and J is less or equal than R. They are in the transmission range of each other. And the nodal degree NDI, or the cardinality of Ni, is calculated as NDI is equal to the absolute value of Ni. That's basically counting how many nodes are around you. The absolute distance between the two UAVs is calculated using the Euclidean formula. Distance Ig is equal to, I mean, square root of xi, xj minus xi squared plus etc. The well-known, I mean, formula. Then the average absolute distance between all the R neighbors of a current UAV is given by ADI is equal to 1 over Ni minus 1, summation from J to Ni minus 1 of the distance Ig. Now, these are the basic, I mean, parameters. Now, in the BICF algorithm, a path detection function to select the best data communication path between UAVs were defined as, I mean, W1, that is a weight assigned to the residual energy, how much energy is left, I mean, in that node, divided by W2 times Ni, the number of neighbors of for that specific node I, times another weight W2, times another weight W3 times the distance basically between them. Now, the use of Ni here is imprecise. as it includes all nodes, regardless whether they are, at a safe distance from the node I or not. And that's a problem here. You cannot, consider all the nodes. We have seen in the previous example that if the nodes are very close, then you cannot consider them as candidates. Now, then the safe zone for collision avoidance is basically given as absolute distance between the two UAVs is redefined as given here. The distance between IG should be greater than delta, the minimum safety distance between two UAVs. Now, in this example here, what we have here is in safe zone. UI is quite, far from all the other neighbors. So, we have a perfect cluster here with a safe, zone. Now, the other conditions that we have here is basically delta must be, much less than R, and the other condition is basically delta should be, or the distance between IG should be between, delta and R. So to be able to have a safe zone, like in this case, and not to get into this situation where, let's say, U1, U2, and U3 are very close to each other. If we consider them, as part of the same cluster, and one of them is, a cluster head, then we can get into trouble, and we can get into basically, a collision that will make the network to fail. Now, the proposed new distance parameter is given by the following. So now we redefine DIS IG as a safe DIG, which is equal to this distance between IG if the distance is basically between R and delta. Now, if it is not the case, then the safe DIG is equal to R plus delta as a penalty, so that it will not be, considered as one of the possible, basically, candidates for, clustering. Now, the new proposed average absolute distance, psi I between the UAVs directly connected to UAVI is given now as 1 over NDI minus 1, summation of D equal 1 to NDI minus 1 of safe DIG. Now, the smaller the value of psi, the closer, the position of the node to the center of the neighbor. Now, another flaw was detected in the both algorithms is basically the fitness function. Fitness function here that is given in the AACL algorithm, dictates that we have, weights assigned to energy residual, the average distance, and the delta differential that we'll see later on. And here, delta differential, basically, delta diff is basically a difference between an ideal degree minus no degree. Note that the ideal degree is parachuted here, and it has no rational. Therefore, it is used, in a fuzzy manner, and it is unfounded. And this will lead to the creation of mini CHs, and will lead to the increase in energy consumption due to increased communication overhead with the CH. Now, a further flaw in the AACL algorithm is the equation of the average distance find that was used, used wrongly, dividing by NI instead of dividing by, NI minus 1, as is, corrected here, in our case. Now, again, in our case, we solve this by using, instead of using 5, we use the equation, 10 instead of 5, that results into no collision. So equation 10 basically is the one that is given here for psi, that is giving basically, using the safe distance instead of using only the distance. So in that case, we solve these problems of these, contributions. Then next, another paper basically is also used as a reference, is basically, presenting a formula for safety degree, YIG, when considering node mobility as YIG equal to R minus DT over R. Again, we found that it is not, accurate, and then we have modified it as SDI is equal to 1 minus 1 over R minus delta safe DIG. Again, we use the safety distance instead of not using the mere distance as it is. Now, the average safety degree is again recalculated, for a UAV using the formula 15. Again, as you can see, using again the concept of safe distance, so that we are always in a safe, setting. Now, next, we have introduced a mobility awareness factor that is given, based on the relative speed of two nodes, Vj minus Vi over Vj, that's the equation 16, and that gives us the mobility awareness factor is given by Mi is equal to e to the power 1 minus Ti. And then this will lead to the average mobility awareness factor that is given as, sigma I 1 over NDI minus 1, summation of J equal to 1 to NDI minus 1, MIG. That means using this mobility awareness factor, so the ability of the nodes to be aware of the mobility of the environment, or the other, let's say, nodes. Now, the residual energy and CH selection fitness function was given as ER equal to EI minus ET, where EI is the initial energy within the node, and ET is the consumed one. Then this again gives us the mobility awareness factor. Now is used to basically compute what we call the fitness function beta I. Beta I is 1 over lambda I times lambda I times W2 times the ERI for a certain node I, that is the residual energy for node I, divided by W3 multiplied by sigma I. Now here, this is the fitness function that is now being used to compute be the best candidate for the CH. Now, a list of beta i's should be maintained in all nodes in a set called gamma I, and then the then the CH would be selected as the one that has an ID, where the beta I is the minimum among all the elements of gamma. So the gamma will be with all the nodes, and the nodes that find itself that it has the minimum one will declare itself as a cluster head, and will assume the role of cluster head and add members to the cluster. Now, this is the cluster head election algorithm. I'm not going to into detail in it. You'll see the paper basically detail. It's basically an IEEE access, available to all to access. And then in addition to this cluster head algorithm that is used, all these formulas that we have just seen right now, we have also made a cluster maintenance and backup utility. And this backup CH selection is carried when the CH is forced to relinquish its role. Now, if there is no CH, so what will happen with the others? So, as a precaution, we select the CH and a backup for the CH. So when the CH, let's say, move into another, absorbed by another cluster, for instance, which is possible, then the backup will be, elected, and then another backup for the backup will be elected, and in this sense, so we can maintain basically the continuation of the operation of the cluster. Now, we did some performance evaluation, and I will go rather quickly here as we are just running out of time. So we did the performance evaluation of the proposed EMAS algorithm in comparison with the BICF and the AICL using MATLAB-based simulation. 100 simulation runs were run with randomized seeds to take off the effect of randomness. And the table gives the parameters that are used for the simulation. Again, you can access this information on the paper basically. As for the results, we have got excellent results as compared with the two competing basically EALCL and the BICF algorithms. This let's say plot shows the cluster formation time required for the different densities of UAVs. With the increase in density, basically the cluster formation time increases. That's quite normal, but we see that the EMAS is outperforming the other two protocols quite clearly. The next one is the evaluation of the energy consumption. For instance, again, with the higher number of UAVs, we have higher energy consumption, and then still the the EMAS, our proposed algorithm, beats all the other two peers. The third one, basically cluster life for different density of UAVs. Cluster life is how long is the cluster is lasting, for instance. And again, with the increase of the number of UAVs, definitely the cluster life will go less as you have more communication to be done. So the cluster life metric denotes the time that elapses from the CH election and cluster formation till the time a new CH is elected for any reason. And this is an indicator of cluster stability. And then we can see that the EMAS has a higher cluster stability than the two others. Then the PDR, that is the packet deliverability ratio, I mean, is again showing that the EMAS is quite superior to the other two candidates. I mean, with clear, I mean, superiority. And the next basically evaluation is the end-to-end delay evaluation. Again, we see that the EMAS is quite, I mean, good performing and quite demarked from the other two, I mean, algorithms in terms of basically performance of EED or end-to-end delay. The next is the effect of the transmission range on the number of living CHs. When we increase the transmission range, so we tend to have more CH living and moving to towards other, let's say, I mean, clusters and being absorbed in other clusters. So we see that, I mean, in our case, the EMAS has the least basically CH living the cluster as compared to the others. And again, another, let's say, another measure is basically effect of the transmission range on UAV reassociation, basically. Again, the association, that means you have UAVs that go, I mean, out of the cluster and can get back. And this is the effect of the maintenance, basically, procedure that, again, shows that our, I mean, proposal is much better than the other two in terms of minimizing, I mean, the number of, I mean, reassociation. And then in the next slide, it shows it is also minimizing the average reassociation time versus the transmission range. No, sorry, this is the only case where, I mean, our EMAS basically has a more reassociation time versus the transmission range, because, I mean, that time is needed to run the maintenance utility, I mean, so that, I mean, we can have a better, let's say, stability of the network. So, I mean, that, I mean, overhead, it comes at a specific cost. Now, that's basically what we had to say about our, I mean, proposal. Now, as a concluding remarks, conventional clustering schemes in high mobility of UAVs do not perform efficiently in terms of network latency and stability. In this work, a FANET clustering algorithm that strives to ensure network stability and improve its power efficiency as proposed. This novel energy and mobility-aware, stable and safe clustering mechanism focuses on improving the overall network stability and safety by employing enhanced parameters related to mobility and safety distance awareness, thus contributing to better cluster stability and higher energy saving. Now, comparative studies with peer has demonstrated a clear superiority. Now we finish with the future perspectives. So we are proposing one way to go is to explore the SDN-based framework to control. Basically, SDN is the, I mean, software defined networking that is based on, I mean, programmability of the networking function, so that we can have on the fly basically decision about the networking function to invoke, for instance. So the SDN is a new framework that is being applied to, I mean, to FANET. The way to explore SDN-based framework to control the obtained FANET clustering using our proposed EMAS algorithm, we, in our, I mean, belief, may enhance the network energy consumption, stability, safety, and may increase its lifetime and better energy efficiency. Now, another path to explore is to go on fuzzy and basically use the fuzzy logic in controlling the fluctuation in distance, the fluctuation in velocity variation, the power estimation, basically, again, I mean, fuzzy estimation to enhance the cluster stability further and to have a better clustering, basically, I mean, setting. Yet another way to go is to, extend, is to consider 3D planes and different flying coordinates and try to solve the stability and safety problem again. So instead of maintaining that all the nodes fly on the same, plane dictated by the mission, so we can make it free, because we can have sometimes the mission will require some nodes to fly at a different, heights and with different coordinates. And then they try to solve the stability problem. So in that case, so we have several issues. That makes the problem a bit more complex and needs, more advanced, features that can benefit from the EMAS and build upon it. With this, I conclude. Thank you very much for your attention, and I will be happy to entertain some of the questions. We have only 5 minutes left to go, and the floor is yours, basically, Dr. Fuad. Dr. Fuad, you're muted again.
Okay, yeah. Thank you very much, Professor Dr. Adel, for this distinguished lecture you shared with us today. It is interesting presentation and informative talk. Yes,
Thank you.
as you said, Doctor, for about the flying ad hoc network, there are many research issues and opportunities in this type of network due to their unique characteristics in terms of the heterogeneity of the nodes and also the mobility and the diversity of the applications requirements. So there are many, there will be many applications, many scenarios that is totally maybe different in their requirements in flying ad hoc network and the
Yes.
type of the nodes itself. So we now we come to the questions and answer part of this session. Like I said, we those who have any other questions to be asked to for Dr. Adel, please write them down in the chat on the comments sections. Actually, we have a lot of questions. The first one of this question, the Prof, for your insightful sharing. Thank you for your insightful sharing. How FANETs help to overcome this pandemic? Yeah.
Yeah, definitely. This is an issue that is already tackled basically by research right now. Basically, the FANET can be used to detect basically patients among a crowd. For instance, if you have, I mean. High precision, let's say, temperature sensing, for instance, that are equipped on drones flying over a crowd, that they can pinpoint basically those who have, let's say, high temperature, or they with a camera, for instance, a high resolution camera, it can pinpoint those who are showing signs of, let's say, the flu, and they are moving within the crowd. This can be used by by these drones basically to help pinpoint those people and ask them to move out of the crowd, for instance. Another issue is basically to have the drones provide, let's say, emergency delivery of required medicine to remote, let's say, patients in remote areas. The applications can be numerous, because you have the possibility of fast deployment of the drones and to the specific target area using basically a Google Map location. This area is quite promising.
Okay. There are also I have my questions here. How
Yes.
actually the cluster node can be selected? Is it online or offline in the
No.
presentation
It's
on the
it's
ground?
dynamically it's dynamically and online. But it's continuous process. Is
Uh-huh.
that that let's say set of hello messages that are being exchanged by between the members is always there, and then inside hello messages, you find the value, beta I, that is the index of fitness, and each one has to maintain all the beta i's in that the gamma set, for instance. And then if it finds itself that it has the lowest, gamma I, then it has to declare itself as a CH. So it is, a fully dynamic and continuous process.
Yeah, okay. So in term of, because this is will need like the hello messages and cooperation among the nodes for the selection. So
Yeah.
is there any countermeasures against the misbehaving or the compromised node that share, for example, false or malicious information, so that the cluster head will be selected in a wrong way, maybe?
Yes, that's another aspect of the research that should be complementing this, is to look at the security aspects, and to look or to use techniques basically that are well known in the security realm. To identify misbehaving basically nodes, and then to include those aspects into the cluster, let's say, selection process. That can be an area of extension.
Yeah. Yeah, also there is one questions from the participant: is data-centric routing algorithm preferred for FANET, and what is the challenges of adopting these types of algorithms? So he talk about the data-centric routing.
Yes, data-centric routing basically could be, used. We didn't talk about the routing itself. Basically, it's just a routing that we have talked about. It is using, the clustering for a better routing, but that routing can be data-centric, no problem. Depends on the application. If you are more, let's say, lean toward the content of the data basically, and then data centric routing would be, the routing of choice. But that does not, let's say, negate the concept of clustering that is helping the routing task regardless of what it is.
Yes. So in term, because the flying ad hoc network, the attitude is different, the mobility is random, like not like in vehicular ad hoc network where there is a predetermined routes. So in flying ad hoc network, the mobility is like random, maybe in the air, the attitude, latitude, and so on. So with these uncertainties, is there a need for mobility prediction to serve with the clustering algorithms of the node to select the cluster head?
Yes, that's what I said in the perspective. Basically, if we have we consider 3D and different flying patterns, and then the flying, let's say, pattern is not dictated, is not pre-recorded, is not pre-programmed, for instance, then that has to be taken into consideration during so you have to include other, let's say, parameters into the choice of the CH, for instance, which one is the best, let's say, situated in terms of the position of all the others to be, a cluster head, in addition to, the other features of safety, and then stability, basically. So that's definitely, an area of research as an extension of the EMAS that can build upon what the EMAS is basically proposing.
Yeah, great. There is also one question. I think you already answered part of it, which is this a centralized algorithm where the base station is responsible for the formation of the clusters? Considering the mobility of the nodes, how does this algorithm tackle the issue when any of the cluster head is out of range from its cluster members?
Yeah, thank you. That's an interesting question. For the first part, basically, it is a centralized. It's not a centralized. It's a decentralized, because, as we have described it,
Yeah.
basically the procedure is executed by all the nodes. And then, the cluster is decided depending on basically a certain, neighborhood, and depends on the transmission range. So it is, dictated by the transmission range. If you are, I mean, I mean, you have let's say 5 or 6 members that are in the transmission range of yours, then those are candidates of the cluster. Then, I mean, among them, so we choose one of them to be, I mean, a cluster head, and the others, they will be called to be members of that cluster. That means if they have another cluster next to them on the other side, then I mean they may belong to this cluster or to the other one, depending on the convenience that they have, and depending on the value of the, I mean, the beta I they have. That's from one side. The second, I mean, part of the question, considering the mobility of nodes, uh, basically the nodes can go away out of the cluster, and that's why we have added the cluster maintenance utility. The cluster maintenance utility means, I mean, it is executed when the cluster is not present, cluster head is not present anymore. That means when the cluster head, for instance, is being absorbed by another cluster to be its cluster head or to be a cluster member of it. And this is done, I mean, dynamically based on those basically, I mean, parameters of beta I, and then the other parameter that we have shown at the end, if you can recall.
Okay.
That's
Okay.
basically dealing with the BCHI and the selection of the what we call the backup, I mean, node. Okay, so it is being dealt with, I mean, at that level.
This is, we have also another question here. I think also you already answered part of it. Most of like most of FANET applications relies on the cooperation among the vehicles. What are the security countermeasures that can address spreading false information by attackers? I think you
Now,
already.
a path of research that's being, I mean, we are pursuing right now is to use blockchain basically for securing the communication between the nodes. Definitely not blockchain with its, I mean, heavy duty, basically, I mean, mining, but I mean, more, let's say, adapted version of the blockchain, which is right now a quite, I mean, a hot topic, applying blockchain to the Internet of Things. So we are pursuing that basically to try to secure the communication between, I mean, these nodes. Another aspect is that you are talking about, I mean, a closed, I mean, network that is, I mean, being connected to the internet through the lead CH, the lead, let's say, I mean, cluster head. That lead, I mean, cluster head, I mean, is supposed to be in the assumption here, I mean, much more, let's say, evolved and much more capable, basically, I mean, drone with high capability and high capacity, with the possibility of processing, where we can implement strong, I mean, let's say, encryption algorithms to allow it to be, I mean, a line of defense, I mean, for the whole FANET.
Okay, actually, that was the last question. So now we reach to the end of this session. I would like to thank our distinguished speaker today, Professor Dr. Adel Ben Mnaouer. Thank you
Thank you very
very
much.
much
Thanks. The pleasure is
for
mine.
your interesting presentation and informative talk, and also interesting topic actually. Okay, thank you, Dr. Adel, and we are grateful for the time and effort you took to share your thoughts, experience with us in this distinguished lecture series organized by Faculty of Engineering, University Technologi Malaysia. In fact, we have several research groups tackling these issues of ad hoc network in manets, VANETs, and FANETs. And this is actually interesting talk, which is inspiring. Alhamdulillah. Thank you for
Thank you.
your contribution and the great sharing session.
Thank you.
Uh,
Thank you to all of you. Thank you for the invitation of and the confidence and the trust. Thank you very much. I am very
you
much
are
honored,
welcome.
and it's I mean, a high pleasure that I have in giving this talk. I mean, and talking to all these nice audience. Thank you very much.
Uh, Thank you very much. For all participants, thank you so much for watching and participating in the UTM Engineering Distinguished Lecture Series. We have many more interesting lectures for you. So until next time, I will say bye-bye now, and Assalamu alaikum wa rahmatullahi wa barakatuh.
Thank you.
Thank you.
Thank you. Assalamu alaikum. Thank you. Thank you very much.